In this video, we're going to learn how to use Newton's method to approximate the solutions or roots of an equation. I'll show you the formula, explain how it was derived, and then work through 3 examples, one involving a polynomial, one finding a square root, and one with a trigonometric equation. Be sure to download the free guided notes to follow along and work through the examples with me. Let's start by learning about Newton's method and the formula that you'll need to use. Newton's method is a technique for finding approximate solutions to an equation. Newton's method can be used to solve polynomial equations, to find the root of an equation, or to solve a trigonometric equation. The reason that we need to find approximate solutions is sometimes a solution to the equation f of x is equal to 0, like the ones up above, can't be found. A solution to the equation f of x is equal to 0 corresponds to a point shown down here where the graph of y is equal to f of x crosses the x-axis. To find an approximate solution, what you do is you start with an initial approximation, usually labeled x sub 0, and then you draw a tangent line to the curve at that point, and the point where that tangent line crosses the x-axis is your new approximate solution. And you continue that process, and the approximations that you get closer and closer to the actual solution. Newton's method gives us a formula for each approximate solution, and we call that approximate solution x sub n plus 1. And it's based on x sub n, which is the previous approximation. I'm not going to go over it, but I have written down the derivation of this formula down here so that you can see where it comes from. Let's walk through an example where we use Newton's method to find the solution to a polynomial equation. We want to use Newton's method to find the root of the equation x cubed minus 2x minus 5 is equal to 0. This is just a cubic equation. We're going to start with the initial approximation x0 is equal to 2, and then we'll continue the process until successive approximations agree to 4 decimal places. Just to make things easier, I went ahead and wrote down the formula for Newton's method. The equation that we solve with Newton's method is the equation f of x is equal to 0. So we're going to let f of x be our cubic equation, x cubed minus 2x minus 5 is equal to 0. Notice in our formula over here on the right for Newton's method that it has an f prime in it. So let's go ahead and let's find f prime at x. F prime of x is equal to 3x squared minus 2. Let's now write down the formula for x sub n plus 1. Those are our approximate solutions. It's going to be xn minus f at xn. So that's xn cubed minus 2xn minus 5, all divided by our derivative, which is 3xn squared minus 2. We're told that we are to use an initial approximation x sub 0 is equal to 2. Let's go ahead and let's find x1. x1 is equal to x0, just looking back at the formula for x sub n plus 1, minus x0 cubed minus 2x0 minus 5, all divided by 3 x0 squared minus 2. Let's now substitute in that x0 is equal to 2. This gives us 2 minus 2 cubed, which is 8, minus 2 times 2 is 4 minus 5, all divided by 3 times 2 squared, which is 4 minus 2. This gives us 2 minus a negative 1, all divided by 12 minus 2, which is 10. And this is then 2 plus 1 over 10. We'll write this in decimal form as 2.1. Let's go ahead and let's highlight that, and then let's go back up and we'll highlight our first approximation as well. Now let's go ahead and find x2. x2 is equal to x1 minus x1 cubed minus 2x1 minus 5, all divided by 3x1 squared minus 2. Since x1 is a decimal, we're probably going to get a decimal for x2, so I'm not going to plug it in. You have to do this on your calculator instead. And when you do, you end up with an answer of 2.0946. I'm including 4 decimal places because our approximations have to agree to 4 decimal places. x2 and x1 don't agree, so that means we have to keep going, and we need to find x3. I'm not going to write down the formula. It's going to be very similar to what we've just written down. When you substitute x2 into the formula, you end up with x3 is equal to 2.0946. Notice that x3 is the same solution as x2, so that means that it is accurate to within 4 decimal places, and we can go ahead and say that our root is approximately 2.0946, and that is accurate to within 4 decimal places. We're now going to walk through an example where we'll use Newton's method to approximate a root. In this example, we're going to use Newton's method to approximate the square root of 2 until successive approximations agree to 4 decimal places. Just to make things easier, I went ahead and wrote down the formula that we're going to be using for Newton's method. To approximate the square root of 2, we need to start by letting x equal the square root of 2. We're then going to square both sides of our equation so that we get an equation that doesn't have the square root of 2 in it. The equation that we use Newton's method to solve is the equation f of x is equal to 0. So we have to get our equation in the same format as this equation. So we're going to subtract 2 from both sides, and we get x squared minus 2 is equal to 0. So we can say that f of x is equal to x squared minus 2. Let's now notice that in our formula for Newton's method, we have an f prime. So let's go ahead and let's find f prime. F prime of x is 2x. We can now write down the formula for x sub n plus 1. That is our approximate solution. Looking up at our formula on the right, it's equal to x sub n minus f of x sub n. So for our problem, that is x sub n squared minus 2, all divided by f prime at x sub n, and that's 2xn. Sometimes when you're using Newton's method to solve an equation, you are given an initial approximation, and then sometimes you're not. In this example, we are not given an initial approximation, so we have to figure that out. So let's just write down that we need to find x sub 0. X sub 0 is an approximation to the square root of 2. So let's go ahead and let's do this. Let's write down that the square root of 1 is equal to 1. And then let's think about a number that we know the square root of. That next number would be 4. So let's write down that the square root of 4 is equal to 2. This means that the square root of 2 is going to be between 1 and 2. So I think a good approximation to start with would be halfway in between. So let's let x0 be 1.5. Now we can go ahead and write down what x sub 1 should be. That is our next approximation. Looking right up here at this formula, x1 is going to be x0 minus x0 squared minus 2, all divided by 2x0. Now what you have to do is take this formula, put it into your calculator, and let x0 be 1.5, and you end up with 1.4167. Let's go ahead and let's highlight that, and then we'll go back and highlight x0. x1 and x0 do not agree, so we have to keep going. So let's find x2. x2 is going to be x1 minus x1 squared minus 2, all divided by 2x1. You put that into your calculator, and we get an answer of 1.4142. Now we compare x2 to x1. Those are similar, but they're not exactly the same, so we have to keep going. x3 is equal to the same type of formula. I'm not going to write it down. You just take x2, plug it into the formula, and here's what you get. You get 1.4142. Notice that this solution is the same as x2. So that means that this solution is accurate to within 4 decimal places. We can then say that the square root of 2 is approximately 1.4142. Just a quick recap. If we go back up to the top, here's what I think you need to remember. I think the hardest part of this problem is creating this equation right here. So just remember, you start with x is equal to square root of 2, you square it, and then you pull everything to the left. We're going to walk through an example where we use Newton's method to find a solution to a trigonometric equation. We're going to use Newton's method to approximate the root of the equation cosine x is equal to x, and then we're going to continue the process until successive approximations agree to 6 decimal places. I've graphed cosine x and x down here so that you can see what the solution looks like. The solution to cosine x is equal to x is where these two graphs intersect, and that's right there. When we use Newton's method, we have to start with an initial approximation. So let's look at this point right here, and let's see what the x value is of that point, and then we can choose an initial approximation close to that value. At this point right here, cosine x is equal to 0. So that means from trig that x is pi over 2, because cosine of pi over 2 is equal to 0. Pi over 2 is approximately 3.14 over 2, so we can say this is approximately 1.5. Let's choose x0 to be a little bit less than 1.5, so let's make it easy, and let's just let x0, our initial approximation, be equal to 1. Newton's method is used to find an approximate solution to the equation f of x is equal to 0. We are given the equation cosine x is equal to x, and we need to now make our equation look like f of x is equal to 0. So let's bring our x to the left, and we get cosine x minus x is equal to 0. So that tells us that we can say that f of x is equal to cosine x minus x, and that's equal to 0. just to make things easier, I went ahead up here on the right and put down our formula for Newton's method. Notice in the formula that there is an f prime. So let's go ahead and find f prime. F prime of x is equal to minus sine x minus 1. We can now then write down the formula for x sub n plus 1. X sub n plus 1 are our approximate solutions. Looking up to the right, it's equal to x sub n minus f of x sub n. Our function is this function right here. So this is cosine xn minus xn. And we're going to divide that by f prime at xn. So that is minus sine xn minus 1. Now we're ready to start getting our approximations. Let's write down that x0 is equal to 1, and we now can find x1. Let's write down the formula. It is going to be x0 minus cosine x0 minus x0, all divided by minus sine x0 minus 1. X0 is 1, and you put that into your calculator, and you get a value of 0.750364. I wrote down 6 decimal places because our approximations need to agree to 6 decimal places. Notice that x1 does not agree with x0, so that means we need to keep going, and we need to find x2. x2 is equal to x1 minus cosine x1 minus x1, all divided by minus sine x1 minus 1. You take x1, put it into that formula in your calculator, and we get a value of 0.739113. Now let's compare x2 to x1. They are fairly close, but they are not the same, so that means we need to keep going. And let's find x3. I'm not going to write down the formula. I think you probably have the hang of it by now. Let's just take x2, put it into that formula, and we get the value 0.739085. Now we compare x3 to x2. They're getting really close, but they're not exactly the same, so we have to do it again. And we need to find x4. You put x3 into the formula, and we get 0.739085. Now we can see that x4 is the same as x3, so that means that our approximate solution is accurate to within 6 decimal places. For our answer, we can write down that the root is approximately 0.739085. And that's it. You've learned how to apply Newton's method to find approximate solutions to equations or roots. To really master Newton's method, make sure to work through several practice problems on your own.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.